This graph represents space as a 2D xy plane, and the vertical axis is the speed of light c times the time t. Usually this axis is used to represent just time, and this way an object at rest in space would move in a straight line in spacetime. Similarly, a planet orbiting the Sun would draw a spiral when moving throughout spacetime. But here, we added the c in front of t, and one of the reasons is because this way all axes have the same unit of measurement, let's say meters for example. Another reason for using ct instead of t is because this choice will give us a very cool symmetry that we'll see later on. This is going to be extremely useful, and we'll see this symmetry through the following example. Imagine we have a point moving at the speed of light away from the origin. This point will trace a spatial distance of 3 times 10 to the power of 8 meters after 1 second. Similarly, the distance traveled in the vertical axis would be 3 times 10 to the power of 8 meters per second times 1 second. Now we do the same for 2 seconds, and we get the point ctx as 6 times 10 to the power of 8 and 6 times 10 to the power of 8. In other words, this specific choice of axis, ct, allows us to trace a line with a 45-degree angle that defines the path of any point moving at the maximum possible speed, in other words, the speed of light.
Anything faster than the speed of light will trace a line, or a curve with tangent line, that has inclination less than 45 degrees. This can be intuitively understood through the fact that the body moves spatial distances that are longer than c-time distances in the spacetime diagram. Anything slower than the speed of light will trace a line or a curve with tangent line that has inclination greater than 45 degrees. This is not only true for points traveling to the right in x and to the right in y, but also to the left in x and to the left in y, or any permutations. This creates a cone, such that everything that is inside of the cone is said to be causally connected to the origin, because it can be reached with a speed v less than or equal to c. Anything that is located outside of the cone is said to be causally disconnected to the origin, because it could be reached only with a speed v greater than c. This is not only true for future events, but for past events as well. The elegance of Minkowski geometry emerges from the fact that all of it, and plus a few other things that we'll see in a bit, come from just 3 simple assumptions. In this spacetime diagram, there are 3 kinds of regions. The existence of these 3 kinds of regions is a direct and exclusive consequence of the following assumptions: that the speed of light is finite, that the speed of light is constant, and that the speed of light is the maximum limit speed in the universe. These 3 regions are s squared greater than 0, s squared equal to 0, and s squared less than 0. The letter s here represents space-time distance, not spatial distance d.
These 3 regions are separated by the cone-shaped figure that we just talked about. S squared can be measured using the Pythagorean theorem. Of course, here we are considering space to be 2-dimensional, but the physically correct assumption would involve a xyz structure, plus the ct axis. It is reasonable that the distance squared from 2 points is positive. So s squared is positive in spacetime. Which means that traveling at any speed v less than c, I can get to the desired point. It is not reasonable, though, that distance squared, so s squared, is 0 in spacetime when using Euclidean geometry, other than the case in which time is frozen, like a picture. And when using Euclidean geometry, we never have that a distance squared in spacetime is negative. So s squared less than 0. It's a contradiction. So Euclidean geometry does not accommodate regions s squared equals 0 and s squared less than 0. The question is, should we change from Euclidean geometry to some sort of alternative geometry? Or should we abandon this understanding of three regions of spacetime? Maybe only s squared positive is possible, and the other regions with s squared equals 0 or s squared negative are just nonsense. Well, again, imagine a point moving at the speed of light. The amount of time passed and the variation of spatial position are clearly not 0. Delta t is not 0, and delta d is not 0. Indeed, if v equals c, we have this. Using Euclidean geometry and this expression, we measure the space-time distance s. S squared is c squared times delta t squared plus delta d squared, reminding you that delta d squared is x squared plus y squared plus z squared. And using this equation, we find out that s squared can be written as 2 times c squared times delta t squared, which is different from 0, since the time interval is not 0. So the Euclidean geometry implies that s squared equals 0 is impossible. Similarly, in order to reach region s squared negative, we need a velocity v that is greater than c. This time, the speed of light c is less than delta d over delta t, which implies that delta d is greater than c times delta t. Using Euclidean geometry and this expression, we can measure the spacetime distance s. S squared equals c squared delta t squared plus delta d squared. And using a very similar reasoning as before, we find that s squared now needs to be greater than 2c squared times delta t squared, which is a positive quantity. So we just found out that s squared cannot be negative. And therefore, Euclidean geometry implies that s squared less than 0 is impossible. In conclusion, Euclidean geometry allows us to describe points in spacetime only inside of the cone, with s squared positive. It does not accommodate for the description of the other two regions, s squared equals 0 and s squared negative. We need another metric. So, a way of measuring spacetime distance s that will cover all three regions. A metric can be thought of as a special ruler that will be used to measure spacetime distances. This is not like your regular Euclidean ruler. Let's derive this metric. So first, s squared positive. The velocity v is less than the speed of light c, which implies that delta d over delta t is less than c. In other words, delta d is less than c times delta t. But this implies that x squared plus y squared plus z squared is less than c squared times t squared. It is okay to use Euclidean metric for calculating spatial distances. There is no contradiction here. But when it comes to space-time distance, it turns out that this will be our new s squared, or metric, rather than the old unsatisfactory Euclidean metric. So the definition of s squared that we are going to use now is c squared t squared minus x squared minus y squared minus z squared. Let's see how this metric, which is non-Euclidean, behaves for the other two regions. So s squared equals 0 now. V equals c now. So delta d can be written as c times delta t. Working on the math here, in a very similar way as before, we can find indeed that s squared equals 0, just as desired. And finally, s squared less than 0. Now, v is greater than the speed of light c, which implies that delta d is greater than c times delta t. And working on the math here again, we can find that s squared is indeed less than 0, just as we wanted. So this formula for s squared works perfectly. It describes all regions. We found our metric, the Minkowski metric. The Minkowski metric can also be seen as a matrix transformation. All we have to do is write it as a multiplication of a vector times a matrix times another vector. And we see that we can recover the original metric by performing the calculations. So this is the Minkowski metric written as a matrix transformation. It's usually denoted as eta. Mu nu represent just the rows and columns, 0, 1, 2, and 3. So 4, because we're describing a 4-dimensional spacetime.
This matrix transformation bridges classical mechanics or Euclidean geometry and special relativity, so Minkowski geometry. And it does so by reconstructing spacetime. At this point, you'll need to change the way your intuition works. This is valid if you're doing either mathematics or physics. If you're enjoying this video, don't forget to like it and subscribe to the channel. Let's use linear algebra in order to understand this new geometry. One of the first things that come to mind when we find a new matrix transformation is to compute its eigenvectors and eigenvalues. If you'd like to know more, you can check out this video on the core of linear algebra, or this one about the core of eigenvalues and eigenvectors, in order to understand how and why we do it. Link in the description for both of these videos. We want to find the eigenvalues and eigenvectors of the following matrix. In order to accomplish that, we need to solve the following equation. For a detailed explanation of how we got to these eigenvalues and eigenvectors, check out the PDF link in the description. This eigenvector represents the c-time direction. Any vector along this direction is preserved. So with eigenvalue lambda equals to 1, under transformations that respect this metric. For the eigenvalues -1, which are threefold degenerate, we have these eigenvectors. These eigenvectors represent the spatial directions. Any vector along these directions flips signs, so with eigenvalues lambda equals -1, under this kind of transformation. The Minkowski matrix transformation is interesting, but again, it only serves the purpose of opening the door to Minkowski geometry or special relativity in physics. What we're actually looking for is a transformation that preserves the most fundamental property of this new geometry, which is the spacetime interval S, regardless of the speed v of the observer. In other words, we want to find a matrix that satisfies this equation. Such a matrix lambda would ensure that the Minkowski matrix eta remains unchanged, guaranteeing that spacetime intervals are preserved under this transformation. But what kind of transformation could achieve this? We can do some math to find out.
This mysterious matrix acts on all vectors of the form ct, x, y, z in spacetime. For simplicity, let's assume that the point moves with a velocity v only in the x direction, so it has a component vx and the other two are 0. This implies that the matrix lambda must be a linear transformation that mixes ct and x components while leaving y and z unchanged. Our goal is to find the values of a, b, c, and d. Plugging this general matrix into our equation and working on the math here, again, check out the details in the PDF link, we find these values for the variables a, b, c, and d. A and d are both the hyperbolic cosine of an angle theta, and c and b are both the hyperbolic sine of an angle theta, where theta here is the angle of inclination of the tilt of the new c-time and space axis after the transformation. We'll clearly see in a bit how and why this tilting happens. By the way, this angle theta is usually called rapidity. A straight world line, so a path in the spacetime diagram, represents constant velocity. The slope of this world line is delta x over c delta t, so v over c, which measures how much space it covers per unit of c time. Since Minkowski space follows hyperbolic geometry, the natural angle measure for this inclination is given by the hyperbolic tangent. So we have that the hyperbolic tangent of theta is v over c. Using this fact, we can work on the math here that you can find in the PDF link. And we find out that the values a, b, c, and d in terms of the velocity of motion v and the speed of light c are these. Therefore, the matrix transformation that we are looking for is this one. Or, more compactly, we can call beta v over c and gamma the term 1 over the square root of 1 minus v squared over c squared. And then we write this matrix this way. This is the Lorentz transformation matrix, or the Lorentz boost, and gamma is referred to as the Lorentz factor. This matrix is important because it describes how space-time coordinates transform between observers moving with a constant velocity relative to each other. It preserves the space-time interval s squared, defined as c squared, t squared, minus x squared, minus y squared, minus z squared. It ensures that the speed of light remains constant, and it keeps the fundamental structure of Minkowski spacetime unchanged. Now, this is not the most general version of a Lorentz boost, because we assumed motion only in the x direction. If we allow the boost to occur in any random direction, with components vx, vy, vz, then the generalized Lorentz transformation matrix looks like this. Yeah, it's huge, I know.
And by the way, even this is not the most generalized version ever, because it accounts only for translations, but not for rotations. The most general version is even more complicated. Of course, this generalized matrix is obtained by combining the boosts in the three directions, but not in a linear way. Check out the PDF in the description below to see a really cool way of deriving this general result. The next logical step would be to calculate the eigenvalues and eigenvectors of this matrix, since they give us information about what directions are preserved in the transformation and by how much its eigenvectors are stretched or compressed. In order to do so, we will first calculate them for the standard Lorentz boost in the x direction, and then we will extend the results for the four-dimensional Minkowski spacetime. That's the matrix we'll work with.
After solving the appropriate equations, we find the following eigenvectors with their respective eigenvalues. For the first eigenvalue, we find the eigenvector 1, minus 1. For the second eigenvalue, we get the vector 1, 1. Graphing these results, we see that one of the vectors gets contracted, while the other gets stretched. All of it takes place along these two gray lines, which, by the way, form the light cone. As a more concrete example, imagine that this is a Lorentz boost such that the point particle that we're studying moves at 90% of the speed of light, so v is 0.9 c. Notice that the velocity of a stationary observer with respect to the particle moving at 90% of the speed of light will be a negative number. In this situation, since they are moving away from each other with velocity v, we'll consider the velocity measured by the stationary observer to be negative v. Using the velocity v, we calculated beta as minus 0.9. Check the PDF. The Lorentz factor is about 2.294. One of the eigenvalues is approximately 0.229, with its eigenvector being transformed into the vector 0.229, negative 0.229. The other eigenvalue is around 4.358, and its respective eigenvector is transformed into the vector 4.358, 4.358. Graphically, we start with the eigenvectors 1 minus 1 and 1, 1, and they get scaled by their respective factors. Interesting, we're slowly drawing the new diagram we get after the transformation. Let's see what happens with the CT and x-axis now. So the CT axis is defined by the vector 1, 0. After performing the transformation, we find the vector gamma that multiplies 1 minus beta. The x-axis is defined by the vector 0, 1. And after applying the transformation, we get gamma times the vector minus beta 1. So the question here is, are these two vectors orthogonal to each other? Let's find it out by performing their dot product. If it results in 0, then they are still orthogonal even after the transformation. Performing the dot product, we find minus 2 gamma squared beta. If v equals 0, so if the velocity is 0, then this results in 0. When v is different from 0, so for example, in our case here, with a negative velocity, the dot product results in a negative number, which implies that the axes ct prime and x prime after the transformation are not orthogonal anymore. Now, performing the Lorentz boost, for many points in the grid of the plane, we get a very good grasp of the dynamics of the motion. This is clearly a hyperbolic spacetime. Of course, we can extend it to 4 dimensions, ct, x, y, and z, describing the Minkowski spacetime. The formula of a hyperbola can be derived from the Minkowski metric, where 1 is the length of the axis here. That's just a definition of a hyperbola. We cannot draw the 4-dimensional case, just a 3-dimensional version of it. But you can use your imagination to try to grasp the idea of extending this diagram to 4 dimensions. And this is Minkowski geometry. And also, guys, do not forget that we have a website where in one of its sections, you can submit your own personal research. Just send it to us via email. More details in the description.
If you like this video, I'm sure you're going to love this one. See you guys there.